Hello students, I am Dr. Tanmoy Biswas. I welcome you all in my channel Chemistry, the Mystery of Molecules. Today's topic of discussion is very interesting. Oxidation by iodine as a reagent, and mainly we shall focus on organic reactions. Okay, so today we shall mainly discuss about the mechanism and one example and one MCQ. So this is the overall topics. This is one of the example. So let's start. But before going to details, one MCQ. In this case, I request you student, please look at the problem carefully, pause the video, try by yourself, and whatever answer you get, please write in the comment box with few words as explanation. Don't hesitate whether your answer will be right or wrong, because remember one statement, self-evaluation is essential for improvement, and for that purpose you should try. And don't worry, at the end of this discussion you will have the right answer. So now let's go to our main discussion. Iodine as an oxidizing agent. So what is the basic idea for iodine as oxidant? This iodine actually belongs to the halogen family, and it is the member of the family like fluorine, chlorine, bromine, iodine, although it is on the bottom compared to fluorine, because first fluorine, second chlorine, third bromine, and fourth is iodine. And you can see the structure of this I2 molecule, because these halogens are diatomic molecule. This iodine contains 3 lone pairs of electron, and this iodine has 1 sigma bond. Okay, so this is the overall this electronic distribution on the outermost valence shell of this iodine. Now mainly I shall say, so it has a tendency to get reduced by 1 unit electron. What do I mean? Iodine atom get one amount of electron and converted into I minus. So in this way iodine got reduced, and whoever is giving this electron, that atom is getting oxidized. So actually overall this iodine is acting as an oxidant, or more specifically if I say iodine molecule takes 2 electron and form into 2 iodide minus. So overall 2 unit oxidation happens by 1 molecule of iodine. I repeat, 1 molecule of iodine. Now, not only that, iodine is actually a bigger in size, and its electronegativity is relatively lesser, although 2.66 value looks like significantly higher electronegative. But if you compare with other halogen like this fluorine, chlorine, and bromine, this is the lowest. So it is easily polarizable, and not only that, you can you can polarize this iodine bond by this delta plus delta minus, and in this way reaction could easily be done on this iodine compared to other halogens. And remember student, one statement, this is, if you compare, this is relatively less reactive. Less reactive means more selective, and in organic chemistry or in any chemical transformation, selectivity is very important. Now finally, iodine can take electron on its sigma star orbital, means actually this is the sigma orbital. So the antibonding of this orbital is the sigma star. So in sigma star it can take 2 electron, and in this way this I bond gets reduced and it will convert into 2 iodide. So in this is the overall strategy for the reaction. So whatever upcoming nucleophile is going to break this II bond, it need to have 2 electrons or 1 lone pair of electrons. Now, so let's come to the examples. Actually student, today we shall discuss 10 examples. 9 are this reaction and 10th one is the MCQ as we have presented. Now in this case what happens, this alcohol, this is actually you may consider, if you don't hydrogen, so this is actually a secondary alcohol. So this is alcohol in presence of iodine, K2CO3 and water, it oxidized into a carbonyl derivative. Now actually iodine is oxidizing agent, we understood. What is the role of K2CO3? Just sometime before what I told, that iodine is going to convert into iodide. So will it remain as anion? No, it will be converted into hydrogen iodide. Okay, so in the reaction medium it will produce this hydrogen iodide, and role of base is to convert this hydrogen iodide into this other iodide solvent. In this case, if you use K2CO3, it will produce potassium iodide, such that the reversibility could be destroyed. and iodine is permanently converted into Ki, means the oxidation state of this iodide is -1. It's a salt. Understood. Water, it's a reaction medium or solvent. 90 degrees centigrade is a mild reaction condition, you may consider relatively mild. Now what is the role of Ki? Ki is actually helping to solubilize iodine, because in water the solubility of iodine is very less. With Ki it forms polyiodide salt, and in this case you can see this Ki react with iodine to produce I3. Or if you want to understand this thing little deeply, iodine minus reacts with iodine and ultimately form these I3 minus. Just you can consider it is an addition complex of this iodide with iodine. And why this happened? Sometime before I told that iodine can act as Lewis acid. So it has energetically accessible vacant d orbital. In that d orbital it can take electron, or another chances is there that iodine can take electron in the sigma star orbital also. So whatever, iodine can accept electron. This is the conclusion of the story. And in this way, these pair of electron, actually what is mean by I minus? One electron extra. Okay, this is the I minus. So that electron is not only delocalized on iodine, one iodine, it is also delocalized in these two iodine too. So in overall the electron negative charge is distributed over these three iodine atoms and gets stabilized. And now you can see that, sir, why potassium? Generally in many examples you will see potassium salt. Why? Instead of potassium carbonate, we could have been take sodium carbonate, and we know sodium salts are relatively cheaper. So why not sodium iodide? Remember student, the size of potassium plus is slightly higher compared to sodium. And if you look at this triiodide salt, it is larger in size. So its size is more. So if anion size is bigger, to get a stable adduct, you need bigger cation too. Anion is bigger, so cation is bigger. Okay, fine. So for that purpose, potassium is better. Now you can say that, sir, potassium is fine. Why not rubidium, cesium, etc.? These two metals, they are bigger than potassium. Yes, it is true. But remember, student, in laboratory, before selecting any reagent, we need to consider the cost of that reagent too. Potassium is relatively cheaper, but these two metals are not. So that's why in every angle the use of potassium carbonate is best. Now let's read whatever is written here. These polyiodide are a class of polyhalogen anion composed entirely of iodine atoms. The most common and the simplest member in this tribromide atom. I guess you can see here this I3 minus. Okay. And the main reason, as I told, this iodine is less soluble in water, but Ki3 is significantly soluble, and here the reaction is carried out in water medium. So in order to make the I2 soluble in the iodine medium, this Ki is added. Now, so what is the mechanism? The mechanism is, for actually base is there to abstract the H. I have explained. Now what happens in case of iodine? There is an iodine bond, so lone oxygen has two lone pairs of electrons, so it attacks and it leaves. Similar way, and means there was Ki initially. After this reaction, one iodide is produced here, and later on there will be this means, if I draw it here properly, this is OI, there is hydrogen, and there is one proton. Oxygen is having a formal positive charge. What this base will do? Base will abstract this proton and make it a neutral, means this one. Okay, and in the next step there is also some base in the reaction medium, so this base can abstract this proton, this bond will come here, and I will leave. Question, why I leaves? Because iodide is a good leaving group, so it leaves. Now in this way what it will produce? It will produce this carbonyl derivative, again another molecule of Hi, and that will be quenched by K2CO3. So due this alcohol to carbonyl is actually 2-unit oxidation, or you can consider in this way 2 unit of electrons are withdrawn or taken, and these 2 unit of electrons are reducing this I2 to 2I minus. Initially HI, but later it will be converted into iodide. So this is the overall chemistry of electrons. Okay, student, please remember this thing carefully. Later on, I am not going to explain everything step by step. So that time this concept will be needed. Now, so let's come to our reaction number 2. This is actually alcohol to directly ester. Okay, how? First, alcohol in presence of iodine is converted into aldehyde, RCHO. And by the way, student, whenever you are trying to convert alcohol into ester, you must take alcohol primary. Why? Because you need 2 units of hydrogen attached to this carbon, and only primary alcohol can fulfill this criteria. Okay, because this is, if you do not have this aldehyde, then you can't oxidize ketone into corresponding ester that much easily. Now, so first this aldehyde, and second aldehyde is oxidized to corresponding carboxylic acid, or you can consider ester. Now, ideally for this purpose, how many of iodine molecule or how many equivalent of iodine molecule needed? Actually, we need 2 equivalent. Okay, but in this case iodine is taken slight excess. Now, you can say that, sir, this is an alcohol, CH2OH, this is also an alcohol, this trifluoroethanol. It's true, but why not this? I shall come this question later on. Not only that, I shall explain about tertiary butanol also. Why we can use this tertiary butanol as a solvent. Now, first step, aldehyde is produced. Second, this aldehyde is further reacted with another molecule of alcohol, and in this case, this is a separate reaction where iodine can oxidize this into the corresponding ester, but in this case 1.2, just look at the value, slight excess. Theoretically 1 equivalent is enough, but for practical purpose 1.2 equivalent is enough, and in this way it converted into corresponding ester. And check the condition, room temperature. Okay, this base needed theoretically 2 equivalent, but taken slight excess, that is 3 equivalent. First one 50 degrees centigrade, so you can conclude that this is actually a milder reaction condition. Okay, so now let's discuss the role of different alcohol as solvent versus reagent. So I shall come in the next slide. First, let's learn about the mechanism, that is alcohol as reagent in the left and alcohol as solvent in the right. Just take alcohol as reagent, means alcohol is directly participating in the reaction. So first step, just same mechanism, I am not going to explain again. Using 1 unit of iodine, it converted into 1 unit of aldehyde. Fine. These aldehyde react with this alcohol under this reaction condition to produce this is, which is nothing but a hemiacetal. I have already discussed about hemiacetal, acetal previously. Please visit for better understanding. Now, if you look at this hemiacetal a little carefully, this part, just look at this part. This is an alcohol and 1 hydrogen is there. So it can also perform the same reaction, first iodine addition to oxygen, then proton elimination to form the final this carbon oxygen bond. Obviously, yes, that is happening. Whatever R was there previously and whatever this part as it is. But after chemical reaction, what does it looks like? This is student ester. So in this way the ester is produced. Now, why I told that alcohol is acting as reagent? Because it is involved in the hemiacetal formation. Now let's go to the second mechanism, that is alcohol as solvent. Solvent means it will help the reagent to be solubilized, but directly it will not participate in the reaction medium, or it will not be attached to the reagent or product at the end. Now, similar way, alcohol in presence of 1 unit of iodine, it converted into aldehyde, and in this case the starting alcohol is participating in the acetal formation. You can see this is the starting alcohol. In the next step, similar mechanism, this carbon OH got oxidized and ultimately produces this ester. Now, what is the difference? Previously CF3 attached to here, but in this case the starting alcohol. So just recall student the Tishenko reaction from one step, aldehyde to ester. In this case, this iodine mediated method, in one step primary alcohol to ester. So that is the uniqueness of this process. Okay. Now let's come to the clarification about alcohol. There are three alcohol, this CF3 CH2OH, this is ethanol CH3 CH2OH, and finally this is tertiary butanol. Now if you look at these two, alcohol has CH2OH, means they are primary alcohol. So both should react similarly or not? Obviously not. Why? If you compare the acidity of this trifluoro containing ethanol or simple ethanol, who is more acidic? Acidic I am talking about this OH bond. Sorry. So this is actually more acidic. Why? Because the CF3 group, this group has strong minus I effect because of the electronegative atom fluorine present in the molecule. Consequently, the donation tendency of this lone pair is reduced. Now just try to recall the mechanism, how the iodine got activated. These lone pair of oxygen given to iodine, then this bond breaks. So in this way reaction initiate. Since the donation capability of oxygen is less because the CF3 group is withdrawing, so it is reluctant to donate. So if it is reluctant to donate, then how it will undergo oxidation by iodine? Actually, just I told at the beginning that this reagent iodine is mild and selective. So under the reaction condition, this trifluoroethanol, this CF3 containing ethanol does not oxidizes at all, although this simple ethanol could be oxidized. So this part you understood. Now let us discuss about this ethanol versus tertiary butanol. So as I told, this hydrogen is needed during the reaction such that this alcohol could be oxidized to carbonyl, but in case of tertiary butanol, no hydrogen is there, so oxidation of this not possible. So directly it cannot participate in the reaction medium. So consequently we can use this tertiary butanol freely as solvent. Just look at this example here. Tertiary butanol is used as solvent for this purpose only. Okay, so for better understanding, I believe I have already uploaded 2 lectures, that is oxidation of alcohol to aldehyde, the basic concept and mechanism, and tertiary alcohol oxidation by chromium reagent, what is the product and how this reaction happens. So please visit for better understanding. I shall provide the link in the description box. Now let's come to a very interesting reaction, that is the iodoform reaction. What is iodoform? Iodoform reaction is ketomethyl react with iodine sodium hydroxide converted into iodoform, or this secondary alcohol having CH3CHOH follow the same. So at the initial stage this alcohol oxidizes to corresponding this ketomethyl derivative and later follow the same pathway. This is the iodoform reaction. By the way, I have already discussed haloform reaction in details, so I am not going to explain this thing here in detail, so you can understand. Just very brief, if I say, first in presence of iodine alkali, these 3 hydrogens are replaced with iodine, so from Ci. After this formation, this carbonyl carbon became very much electron deficient. Consequently alkali attacks and it opens up, this intermediate is produced. Later on this pushes and Ci3 leaves as Ci3 minus. Why? Because the withdrawing effect of iodine, means the halogen, helps to stabilize the negative charge on this carbon. Later on it protonates and produce this CHI3 or iodoform, student. By the way, why this iodoform is important? Because this iodoform is yellow in color and it is a precipitate or white solid compound. So by watching the yellow precipitate or yellow crystal produced during the reaction, we can conclude that the organic sample which have gone through this test contains this ketomethyl group or this CH3CHOH, means this secondary alcohol or not. So this is the iodoform test. Now just let's extend the concept. Same thing, everything. Instead of water, means just try to recall that the alkali got attack into the reaction medium. That's why we got this carboxylic acid or carboxylate. Now fine. Instead of alkali, if we take another X minus, then this X minus will do the attack and ultimately what it will produce? ROOX in this way. same thing is actually happening here. So ammonia is playing the role of that nucleophile. Means in the reaction medium, what it produces, that will react with ammonia and produce this is actually, you can consider acid amide. So in this way acid amide could be produced. Now let's look at the mechanism. Just similar way this CI3 is produced, triiodocarbonyl derivative. Later on ammonia is acting as nucleophile to open up this tetrahedral intermediate, then it pushed this CI3 leaves, and this is the iodoform, and along with the iodoform what it is produced, this is acetamide. This is the mechanism, I guess little easy mechanism. Now let's come to a little different type of mechanism, that is iodine mediated amine to amide formation. Means see, this is actually a tertiary amine, you can consider. This is getting converted into amide, tertiary amide. How this happening? See, in this case little excess of iodine needed, bicarbonate, and later a solvent. Now how this reaction is actually happening? See student, as I told, iodine can act as Lewis acid. So in this case amine is acting as a base. So that's why this iodine amine adduct formation happened. So in the first step you can expect that this lone pair of nitrogen will attack the iodine, it will leave as like the previous mechanism, and it will produce this, and one molecule of HI. This HI will be consumed by this bicarbonate. Fine. In the next step you can see that this has a hydrogen. So this hydrogen could be abstracted by the base, and ultimately it will come here, and iodine will leave, and nitrogen will have the positive charge, because nitrogen is, it's a moderately electronegative compared to halogens or carbon, intermediate type, and nitrogen can keep the positive charge on itself, and it could be tetravalent. Okay, so that's why it produces this. This is nothing but another, say, iminium. We know iminium, and it is significantly higher electrophilic, because you can consider a canonical form, that is, this is Bn, this nitrogen, that is the 6-member ring, and this double bond could be withdrawn here. So nitrogen is neutral, having lone pair, the adjacent carbon is having positive charge, and that's why this carbon can act as the electrophilic center. So in the what happened in the reaction medium is water dioxane, so water will attack here and it will open. Similar way, so it will produce this amine alcohol derivative. Now interesting thing is that next step also iodine can react. Just remember 7.5 equivalent, too much excess. Okay, so in the next step similar process will happen. This iodine will attack, again leave. Just this is a Lewis acid base, I am not going. So here directly, second again there is another proton, so it will be abstracted, it will go, it will leave, and ultimately it will produce this. Now a question may come in your mind that, sir, there is one hydrogen, it's true, there is another hydrogen, why the reaction didn't extract this HX? Because student, ultimate the product is conjugated and relatively stable. Not only that, it can have a tautomer. Tautomer means it can push here, it can open. So in this way it will be converted into amide, but that thing is not available if this HX proton is abstracted. So that is the reaction why this proton was not abstracted. Now let's go to the number 6 reaction, that is iodine mediated homologation of carboxylic acid, or more specifically if I say lower, means this is one carbon reduction. You can see this is CSIR, so reduction, and ultimately it produces also carboxylic acid. If I ask you, can you propose or tell me another reaction where the carboxylic acid number could be increased? Please write in the comment box. Means if you take a RCOOH, using that reagent you can convert RCH to COOH. What is the reagent? Please remember, write in the comment box. There are many, so whatever you think right, please write in the comment box. Now let's discuss how this reaction happening. So student, before going to details, just check what are the byproduct, carbon dioxide and dimethyl sulfide, and in this reaction dimethyl sulfoxide is used as solvent and reagent, and along with that obviously iodine. So what is actually happening? In this case, first iodine is converted into HI. How? See, we know that carboxylic oxygen can do significant nucleophilicity. You can say that, sir, this oxygen is more nucleophilic. I agree, it's true, but reaction will have a fate when these oxygen will act as a nucleophile. So how you can expect that this oxygen will attack? So this is the iodine-iodine bond. So it will push, it will leave. Ultimately, this means what it will produce? pH, this double bond OI. Now, when you are talking about a carboxylic acid, this carboxylic acid has an equilibrium with its deprotonated form. So in this case, I would say COO minus, and these means carboxylate anion plus proton. So because we know, because of this anionic intermediate formation, the carboxylate, this is not that much electron deficient, agree, but when it is converted into corresponding OI, so no proton is there. Now the whole group, I am saying this group is actually a significantly strong withdrawing in nature. So what you can expect? That it will be more efficient for enolization of these alpha proton. Okay, so that is the reason why this enolization you can expect. So in the next step, what you can expect? That pH double bond this OH OI, fine, and this is what it is, student. It is actually an activated alcohol or enol. By the way, I have already discussed many lectures on silyl enol ether, in which case this carbon act as a nucleophilic. This carbon is nucleophilic electron. Similar thing you can expect here. So what you can expect? That this oxygen will push its lone pair, and these double bond will attack this iodide and it will leave, and in this way these alpha iodo derivative will be produced. Fine. Now if you look at this part little carefully, so you can say, sir, this is nothing but alpha halo or iodo ketone, and we know alpha halo ketone can undergo SN2 reaction very efficiently, and by the way, I have already discussed a dedicated lecture on this topic. And in this case, who is acting as a nucleophile? Dimethyl sulfoxide oxygen. Why? Because we know dimethyl sulfoxide has another canonical form, means this is O minus, is plus, this is methyl. So you can think that these O minus can act as nucleophile, and these iodine can leave, because iodine is a good leaving group. So this is DMSO adduct, means SN2 type reaction. Now in the next step, what is possible? See, when this iodine leaves, so in that reaction medium there is iodide, so that iodide can attack this Y. If you look at the reaction, this is OI. So after nucleophilic attack, what you can expect? That this will be O minus. This is resonance stabilized carboxylate anion. So stable means that's why this iodide attacks here and it produces this carboxylate. I am showing this thing stepwise. I know little tricky. So this is O, this is S, so this is dimethyl. Now this is O, this is O minus. It will be produced. Now these can undergo decarboxylation. How? First it will push here, it will open up and it will come back. Come back means then it will produce a carbon ion. Here I am showing stepwise, students. Stepwise doesn't happen, it happens instantly. So this is a minus, this is O, this is S, this is 2-methyl. Okay. In next step it can push and this can leave. Means in this way it will produce this aldehyde and this will produce dimethyl sulfide. Now another interesting point. Remember student, DMSO or dimethyl sulfoxide has boiling point near about 180 degrees centigrade. Okay, because of this polarity, this oxygen. But when it is converted into dimethyl sulfide, it is very low boiling. Not only that, decarboxylation produces carbon dioxide, so both comes out from the reaction medium as gas, and in the reaction medium this aldehyde is remain, and we know this aldehyde could be oxidized to corresponding carboxylic acid by iodine. Just some time before I have explained. So in this way it will produce another carboxylic acid. And why I am saying one carbon reduced? Because see, this carbon dioxide came out from the reaction medium And remember students, CO2 elimination is a favorable process. Why? Because carbon dioxide is a very stable molecule, so entropically this reaction is favorable. Second point, enthalpically favorable, and one gas is coming out from the reaction medium, means the entropy of the system is getting increased. So if you look at the Gibbs free energy equation, delta G equal to delta H minus T delta S, overall the delta G became negative. Why? Because due to heat release, stable molecule formation, delta H negative, temperature is relatively higher, near about 100 degree, like 120 degree, and delta S positive because one gas is coming from one molecule, actually two molecules, or in this case 3 molecules produced. Okay, actually I shall not say that 1 2 3, 2 to 3 molecules produced. So entropically this is also favorable. So that's how the reaction is favored. Now let's come to the another example, alkyl halide to nitrile conversion by iodine. This is the Rx, alkyl halide. So in this case, this Rx equal to Cl, Br and I. It reacts with ammonia and iodine 2.1 to 2.4. Just alcohol and alkyl halide same oxidation state. Alcohol to aldehyde 2 unit, means 1 unit of iodine needed. Aldehyde to carboxylic acid another 1 unit. So overall we need 2 unit. And these nitrile and carboxylic acid are similar in oxidation state, because this you can see this, so their oxidation state both are same. You may consider this is +3, so they are redox point of view equivalent. So minimum 2 unit needed, and in this case written 2.1 to 2.4. so from redox count also this is true. So let's now how the reaction is happening. In this case, first ammonia is acting as nucleophile using its lone pair of electron via SN2 type reaction. It opens to produce this primary amine. In the next step, iodine reacts with nitrogen similar way like the alcohol, this Ni bond formation. Second, this hydrogen is removed, means abstracted. Ammonia is acting as a base here because ammonia is taken large excess. So first it will produce this imine similar like a primary alcohol to aldehyde. In the second phase, this nitrogen also has one lone pair of electrons, so it can react and again with iodine. So in this way it will produce this nitrogen iodine bond. In the next stage this proton will be abstracted, it will come and it will leave, and in this way it will produce nitrile. So this is an interesting example, means this is iodine mediated oxidation of alkyl halide to nitrile. Very interesting, I like it. Now let's go back to the next example, reaction number 8. We have total 9, another one more. So first aldehyde react with 1 unit of ammonia. This is ethylene diamine 1.1 equivalent, slight excess. So what happens? First it will convert into Schiff base, then reaction will continue. And if you look at how many equivalent of iodine needed, 1.25, means 1 unit of oxidation you will observe. So I shall explain. And K2CO3 as a base, and tertiary butanol C here used as a solvent too, because of the same logic. So how this reaction happens? First this aldehyde reacts with ammonia, and this is actually imine or Schiff base formation. By the way, I have already discussed a dedicated lecture for Schiff base formation. You may visit for better understanding. Now this Schiff base, next time what happens? If you look at the position, this is 1 2 3 4 5. So cyclization there is a chance, because this ammonia can act as a nucleophile and attack this imine and open. And we know intramolecular reactions are always both thermodynamically and kinetically favored. So that's how it will produce this saturated thing. Till now no iodine mediated oxidation is observed. Now in this step this nitrogen lone pair is available, so it will react with iodine in a same fashion. This, and ultimately it will produce this Ni bond. This Ni bond, this hydrogen could be abstracted and it go. So it will produce this. And by the way, you can ask me that, sir, why this hydrogen? There is another hydrogen also. This hydrogen. So if this hydrogen is abstracted, what you can expect? This is N H, this is N double bond this. But student, if you compare this versus this is more conjugated. Why? There is a resonance, means these lone pair could be donated here and it can open. So R, this is N, this is N minus this, and here this is hydrogen, this, and having a positive charge. So this resonance possible. Resonance means delocalization means stabilization, and this stabilization is absent in this canonical form. So that's why this path will not be followed. And this is, students, similar way using this hypervalent iodine reagent, it can further oxidize this product produced to corresponding imidazole derivative. Right now we will not discuss about this hypervalent iodine reagent, we will discuss in some other videos. Now let's come to the last reaction of today's discussion, that is iodine mediated N-N bond formation. It's interesting, reaction 9. So this is and actually, student, this is very interesting because transition metal free N-N bond formation. So this way, and what are the reagent? Iodine, potassium iodide, Ki3, potassium carbonate. So same like the previous at the beginning one. So how this reaction is done? So first these nitrogen attacks. Now question, why? For that you need to understand one basic concept, means if you take a simple amine, primary amine versus an imidine like this is NH2, this is NH, in which case the nucleophilicity of nitrogen is higher. Obviously in case of these nitrogen. Why? Because there is a canonical form possible, so it can push and it can open. So because of this canonical form, these nitrogen have higher electron density. So if its electron density is higher, then it can act as a better nucleophile. So that's why you can see these lone pair, actually this through this lone pair, but ultimately this proton bond goes and it attacks this iodine. And why this Ki3? Medium is not organic, so that's why Ki3, same reason at the beginning. So first it will produce this Ni bond. Now this thing is very familiar. What is happening in the next step? This is actually a intramolecular reaction. As I told some time before, intramolecular reactions are both kinetically and thermodynamically favored, and 5-member ring formation is favored. This is 1, 2, 3, 4, 5. Here also 5-member ring formation. So in this way this compound will be produced. Now after this nucleophilic attack, this nitrogen is having a positive, it's a pyridine derivative you can consider. So in the next step, base will abstract this proton, it will come here, it will come and it will go. So in this way you can say that, sir, aromaticity is disturbed. It's true, but in this way this proton will be produced, because if nitrogen stable valency is 3, it could be 4 but cationic, but charge separated species are not that much stable. And this is a not simply nitrogen, this is actually a triazole. Okay, this is, or more specifically if I say 1, 2, 4 triazole, there is another triazole, 1, 2, 3 triazole, means in the click reaction I guess you people have seen it. Okay, so this is the thing. So that's a different issue, we will discuss some later video about 1, 2, 3 triazole. So in this way this product will be produced. This part is about some other product formation, we will not discuss too unnecessarily now. So in conclusion, what you have learned today, that iodine is a good oxidizing agent. It is a mild, that is relatively less reactive, so it is more selective. This is a very important statement, student. Less reactive reagents are often more selective. And one molecule of iodine is responsible for 2 unit oxidizing agent, because one molecule have 2 iodine and each iodine takes 1 electron. So overall 2 unit oxidation. Lone pair of electrons can act as an efficient nucleophile, for example this nitrogen, oxygen, if there is proper energy matching, because some X lone pair attacking the nitrogen, if their energy doesn't matches properly, then reaction will not happen. And the most important thing we observe in organic chemistry is that iodine is softer in nature, so it can act as both good nucleophile as well as good leaving group, and that's why iodide anion you will see in many cases used as nucleophilic catalyst. Okay, this is a very interesting term, nucleophilic catalyst. By the way, I have already discussed some videos about this, some kind of this like imidazole as catalyst in ester hydrolysis, those things, so you may visit. So this is a very interesting term, nucleophilic catalyst. So let's come back to our MCQ. What is the major product of this reaction? So this is actually a propargyl alcohol derivative attached to this thiol. Reaction with iodine and sodium bicarbonate. By the way, student, this condition is similar like iodolactonization reaction condition, but it is not. I've already discussed about iodolactonization. You may visit for better understanding. This is iodolactone formation. Okay? No. So in this way, it will produce during the reaction, and there are 4 options. So let's learn the mechanism. Iodine can react double bond efficiently because iodine acts as a Lewis acid, so double bond can attack the iodine, and ultimately it can form beige iodonium compound, and similar properties observed for triple bond or alkyne too. So in this way it will produce this beige iodonium derivative. Now in this case, if you look at, there is OH versus SH. We know the sulfur is a better nucleophile, so SH will attack. Now it is actually, student, intramolecular reaction because these both SH and this beige iodonium cation is in the same molecule. So where the reaction will happen, attack here or here. Now for that purpose, I request you please follow this strategy, this numbering 1 2 3 4 5. So if the attack happened in the position A, then there will be 5-member ring formation, whereas if the attack happened in position B, there will be 4-member ring formation, and we know 4-member ring is associated with significant amount of more ring strength compared to 5-member. So what will happen, that this lone pair of sulfur will attack this position and it will open. So ultimately it will produce this, and in the next stage, in presence of base, this proton will be this OH will be abstracted along with this hydrogen. And what is the driving force? Obviously aromaticity, because it is a thiophene derivative. So this is the product, and previously there was 2 methyl here, so ultimately this dimethyl, 1 iodo, and there is another group. So now see, this dimethyl 1 2 position fine, 3rd position attached to this triple bond, there will be iodo attached to pH. So this is not possible. This is not possible. Actually possible, but this is oxygen. It is not possible. There should be sulfur. So sulfur pH iodo. So option D is the right answer. Okay. And this is also not possible because aromaticity is not gained, as I told. It will be instantly abstracted to get the aromaticity. Now if this question appear in your exam less than 30 seconds, how can you get the right answer? First of all, you need to understand that iodine addition with triple bond will happen and it will produce beige iodonium cation. Fine. Second thing, intramolecular reaction, just count 1 2 3 4 5. This much amount is enough. So 5-member ring formation will happen, and there will be sulfur will be inside the ring. So option A and B gone. Now who is left? Option C and D. If you look at this C and D, okay, there is an aromaticity possible. Aromaticity is a huge stabilization energy, and thiophene is significantly stable aromatic compound, so it's not possible. D. So less than 30 seconds using these tricks, you can end up the right answer. But for that purpose, student, more study and more practice, and finally cool mind in the exam hall is essential. So this is the end of the discussion. Thanks for watching. I believe this video may be useful for you. Please write your opinion in the comment box, and please visit my another channel, Climate and Chemistry, where I upload global warming and climate change related videos. So stay happy, stay blessed. See you in my next video. Bye bye.